So let's just look at a couple more examples. The first being cosine of x. So let's look at the Taylor series expansion of cosine x about a equals 0. So cosine of x is equal to cosine of 0, and then we have to take the derivative, so that's the 0th order term. Then we have to take the derivative of cosine, which is minus sine of 0 times x minus 0. And then the second order term is minus cosine of 0 times x minus 0 squared all over 2 factorial. The third order term is sine 0 of x minus 0 raised to the third power over 3 factorial, etc. And this gives 1 minus 0, because sine of 0 is 0, minus cosine of 0 is 1, is we get x squared over 2. We get another 0 with the sine 0, plus 0, plus x 4 over 4 factorial, and so on. So this gives the expansion of cosine plus 4x raised to the 4th power over 4 factorial. And we would carry this out to infinity to get the exact approximation of cosine function, of cosine. And you'll notice that since x is raised to an even power, then each term will have the same value regardless of whether x is positive or negative. So even powers, or even exponents, make for a even function. Okay, we talked about cosine being even, and this is another expression to illustrate that it remains even as we take this expansion. The expansion of sine x is equal to, gives x minus x cubed over 3 factorial plus x raised to the 5th over 5 factorial, and so on. And you can see that these are odd powers, and they yield an odd function. When x is positive, x raised to the odd power is positive. When x is negative, x raised to the odd power is negative. Okay, and actually I wanted to mention, some of you may have heard or used the binomial series. And the binomial series is just a special case of Taylor. It's just this, it's just the Taylor series expansion of 1 plus x raised to the n power about a equals 0. So 1 plus x raised to the n power is equal to 1 plus n times x plus n times n minus 1 raised to the x squared or times x squared over 2 plus n times n minus 1 times n minus 2 x cubed over 3 factorial. And the sum continues. So the binomial series isn't any special series you need to memorize. You can just know that it's a Taylor series of x plus 1 plus x raised to the n power about x equals 0, and you'll get it. Okay, so that's a summary of the Taylor series. Taylor series becomes useful, for example, if we want to, if we have a function, for example, x plus 1 plus x to the n power, and we want to linearize it to solve a problem when x is very close to a. So if x is very close to a, we could approximate it as 1 plus n to the x, and using manipulating our problem with a linear function is oftentimes easier than manipulating our problem involving the full function. So it's valuable when, in this case, when x is very small. The Taylor series approximation also is relevant when we discretize a numerical or discretize a partial differential equation using the finite difference approximation. The finite difference approximation is a powerful numerical method for solving differential equations numerically, and that's another application of the Taylor series expansion. Okay, well I'll wrap it up right here on Taylor series.